Imagine, just for a second, walking into the largest sports stadium on Earth.
Okay.
Like it's this colossal structure, right?
Right.
Capable of holding well over 100,000 people.
Oh, massive.
Right, massive. And you know for an absolute mathematical fact that the home team playing today is wildly popular.
Yeah.
I mean, the statistics dictate that every single seat should be sold out. Standing room only.
Like, you can't even get a ticket.
Exactly.
Yeah.
So you walk through that dark concrete tunnel, you step out into the sunlight, you look across the sweeping stands, and it's just empty.
Completely.
Not a single person. There isn't even like a stray hot dog wrapper blowing in the wind. There's no usher. It's just echo and complete silence.
Yeah.
And the most unsettling part isn't just that the stadium is empty right now. It's the sudden realization that the gates have been open for business for billions of years and literally nobody has ever shown up.
Wow. Yeah, that is a deeply unsettling image. And I mean, it perfectly encapsulates that visceral unease at the heart of our discussion today.
It really does.
Because you're describing the absolute definition of an existential void. I mean, we look up at the night sky and we naturally just project our own bustling, vibrant reality right onto it.
Of course we do.
We expect this cosmic forest teeming with life, but the actual empirical data we gather from astrophysics and astrobiology, well, it paints a picture of a terrifyingly silent landscape.
Which brings us to the mission for this deep dive. Because today, for you listening, we are taking a massive stack of research, historical documents, scientific papers, and we are going to explore what is arguably the ultimate cosmic mystery.
The big one.
The biggest. We are unpacking the Fermi paradox. We're going to explore exactly why the universe feels so utterly empty when all the mathematical probability screams that it should be crowded.
Right.
And we are going to map out the mind-bending, the terrifying, and honestly awe-inspiring possibilities for where everyone actually is. So, okay, let's unpack this.
Let's do it.
And to do that, I want to set the scene, sort of like a movie opener, to show how this entire framework began.
Oh, please do. Because the origin story of this paradox is, well, it's almost as fascinating as the science itself.
It is. Okay, so it is the summer of 1950. We're at the Los Alamos National Laboratory down in New Mexico.
Ground zero for the Manhattan Project.
Exactly. The birthplace of the atomic bomb.
Yeah.
So you have a concentration of literally some of the most formidable intellects on the entire planet, just, casually walking around the campus.
Just another Tuesday.
Right. And 4 of these absolute titans of physics are taking a stroll to the Fuller Lodge for lunch. You've got Emil Konopinski, Edward Teller, Herbert York, and Enrico Fermi.
Now, Fermi, by the way, already has a Nobel Prize at this point.
Right, he's a big deal.
A very big deal. And he is legendary among his peers for his ability to do these rapid, incredibly accurate estimations just in his head.
The Fermi problems.
Yes, what they call Fermi problems. He was known to ask his students these seemingly impossible questions like, how many piano tuners are there in Chicago?
Just to mess with them.
Well, just to test their ability to logically deduce a highly accurate answer from very basic assumptions.
That's amazing. Okay, so that is exactly the kind of mind we're dealing with here. So they are walking to lunch, and they're casually chatting about a recent cartoon they saw in the New Yorker.
Right.
And the cartoon was basically a joke about a recent spate of missing public trash cans in New York City. The artist had drawn these little green men unloading the stolen trash cans from a flying saucer.
Which is pretty funny.
Yeah. So this sparks this breezy, casual debate among the physicists about the actual feasibility of faster-than-light travel. They bat the physics back and forth, they arrive at the lodge, they sit down, order their food, and the conversation just drifts to entirely mundane topics.
As it does.
But then, out of nowhere, Fermi just looks up from his meal and blurts out, "Where is everybody?"
And Edward Teller's recollection of that exact moment is incredibly revealing. He noted that Fermi's question was entirely divorced from the immediate conversation.
Right, they weren't even talking about space anymore.
Exactly. He didn't say aliens. He didn't reference the flying saucers from the cartoon. He just asked where everybody was. Yet, Teller said, general laughter immediately erupted around the table.
They got it.
Every single physicist sitting there understood instantly, without a shred of additional context, exactly what Fermi was calculating in his head.
They knew he was talking about extraterrestrials. And the reason they intuitively made that leap so fast is tied to this foundational concept in astronomy that, we really need to lay it out for the listener right now.
Yeah, we are talking about the mediocrity principle.
Which sounds like an insult, honestly.
It does sound pejorative, yeah, but it's actually an assumption of utter typicality.
Hmm.
The mediocrity principle basically asserts that there is absolutely nothing special, privileged, or unique about Earth or our solar system.
Right.
We reside on a standard, rocky planet, which orbits a run-of-the-mill, middle-aged G-type main sequence star.
Just totally average.
Totally. And that star sits in a completely typical spiral arm of a stunningly average barred spiral galaxy.
So we are essentially the cosmic equivalent of a suburban cul-de-sac.
That is a very apt way to put it, yeah. And so the logical extension of the mediocrity principle is that if the physical and chemical conditions that catalyze life happen here in this incredibly average, unremarkable corner of the universe,
Then it should happen everywhere else.
exactly, those exact same conditions must naturally occur in all the other average corners of the universe.
And the sheer volume of those other corners is, frankly, what breaks the human brain. I mean, to really grasp the weight of Fermi's lunchtime question, you have to look at the numbers outlined in our source documents.
The numbers are staggering.
They really are. In our home galaxy alone, just the Milky Way, astronomers estimate there are roughly 200 to 400 billion individual stars.
And again, that is just our immediate local neighborhood.
Right. Then you zoom out, you look at the observable universe. The current cosmological estimates put the number of stars at 70 sextillion.
Which is hard to even picture.
It's impossible for anyone trying to visualize that.
Yeah.
Write a 7 and
Yeah.
then put 22 zeros right after it. I mean, our brain just did not evolve to comprehend numbers of that magnitude. We evolved to count like predators in a bush, not stars in a supercluster.
Exactly. Which is why the paradox requires another dimension to fully appreciate. It's not just the spatial scale.
All right.
It is the temporal scale, the time. The universe is estimated to be 13.8 billion years old. But our particular star, the Sun, is a relatively recent addition. It formed roughly 4.6 billion years ago.
And that is the kicker. Because there are star systems out there that are billions of years older than ours.
Billions.
Which means if that mediocrity principle holds up, there could be rocky planets out there that developed life billions of years before Earth even cooled down from a molten sphere of magma.
Just consider the implications of a billion-year head start. Think about it. Human civilization went from the Wright brothers at Kitty Hawk to landing Apollo 11 on the moon in, 66 years?
Less than a single human lifetime.
Right. So imagine a civilization with a million-year head start, let alone a billion. Astrophysicist Michael Hart actually explored this temporal problem formally back in 1975.
Okay.
He calculated the expansion rate of a hypothetical spacefaring civilization.
And what did Hart find when he ran the numbers?
Well, he found that even if a civilization only achieved incredibly conservative speeds, let's say just a fraction of the speed of light, using propulsion technology that is theoretically within our own current grasp.
Like stuff we could build today or soon.
Essentially, yes. They could send out colony ships to nearby stars. Those colonies arrive, they establish themselves, they build their own ships, and they expand outward.
Like a wave.
Yes. And even accounting for the massive distances between stars, Hart demonstrated that a civilization could completely traverse and colonize the entire Milky Way galaxy in just a few million years.
Which sounds like a long time. I mean, a few million years is an eternity to an individual human.
Yeah.
But on a cosmological timescale, it is a rounding error.
It's a blink of an eye.
It really is. So if they could have expanded across the galaxy, and they've had literally billions of years of time to do it, where are they? Why are our skies totally empty? Why haven't they arrived?
That is the core of it.
Because the Fermi paradox isn't just some philosophical musing about whether alien life exists. It is this violent, irreconcilable clash between incredibly high mathematical probability and absolute zero observational proof.
And to bridge that gap, to understand why we expected that cosmic stadium to be full in the first place, we must move away from Fermi's casual lunch conversation and actually examine the mathematical framework scientists use to calculate these probabilities.
Right, the math. We're talking about the Drake equation.
Yes.
Formulated in 1961 by astronomer Frank Drake ahead of the very first scientific meeting on SETI, the search for extraterrestrial intelligence.
Hey!
Now, I want to promise you listening right now that we're not going to turn this deep dive into a dry mathematics lecture.
No chalkboards required.
Exactly. But conceptually, the Drake equation is brilliant because it essentially functions like a massive cosmic filter, or like a funnel.
Right, a probabilistic funnel that attempts to quantify the completely unquantifiable.
It starts super wide, First, you calculate the average rate of star formation in our galaxy.
Yeah.
Then, you multiply that by the fraction of those stars that actually have planetary systems. Next, you look at the fraction of those planets that have an environment capable of supporting life.
Moving further down the funnel.
Right. Then, what fraction of those habitable planets actually develop life? And of that life, what fraction evolves into an intelligent species?
Right, not just bacteria.
Exactly. And of those intelligent beings, what fraction develops the technology to actually release detectable signs of their existence into space? And then finally, the most crucial and sobering variable of all.
Hmm.
What is the lifespan of such a technological civilization? Like, how long do they broadcast before they just go silent?
It is a supremely elegant way to organize our ignorance.
I love that phrase from the source. But the word ignorance is doing a lot of heavy lifting there, isn't it? I mean, isn't the fatal flaw of the Drake equation that it requires us to plug in numbers we simply do not have?
Oh, absolutely. That is the core vulnerability of the equation.
Good.
Because we have excellent observational data for those first few variables.
Right.
We know star formation rates.
Yeah.
Thanks to modern telescopes, we know exoplanets are ubiquitous. But the deeper you go into that funnel, the data just vanishes.
It just disappears.
The fraction of planets where life actually appears, we don't know. The fraction that becomes intelligent, no idea. The lifespan of a civilization. We have a sample size of exactly one.
Us.
Earth.
Earth. And when you have an equation that multiplies hard astronomical data by complete biological guesswork, you run straight into what the source material calls the overconfidence effect in probabilistic reasoning.
Because human cognitive bias completely hijacks the math at that point. Because the variables are unknown, scientists just end up plugging their own psychological optimism or pessimism right into the equation.
And the text highlights this dichotomy perfectly. You had optimists like Carl Sagan. He looked at the Drake equation, estimated generous values for life and intelligence, and concluded there could be anywhere from 1,000 to 100 million advanced civilizations currently active in the Milky Way. Millions of them.
But then you flip the coin, you have physicists like Frank Tipler and John Barrow who looked at the exact same mathematical formula.
The same equation.
The exact same one. But they applied very conservative, pessimistic estimates to the biological leaps required for intelligence. And their result: the average number of advanced civilizations in a given galaxy is significantly less than one.
Wow.
According to their math, humanity is likely entirely alone in the observable universe.
What really fascinates me about this divide is the historical context that our source material provides. Because researchers Dennis Danielson and Christopher Graney, they argue that our cultural optimism, this deep-seated, unshakable assumption that the universe just must be teeming with life, it isn't actually rooted in modern empirical science.
Not at all. It predates modern science by centuries. It stems from 17th and 18th century philosophical and theological frameworks.
Because during the Copernican revolution, when humanity finally realized Earth wasn't the center of the universe, this theological presumption kind of filled the void.
Exactly.
The prevailing thought was that a divine creator would never design a universe filled with all these magnificent, swirling planets, only to just leave them barren and empty. It was seen as an insult to divine efficiency.
God wouldn't waste space.
Right. So early astronomers just naturally assumed everything was inhabited, like William Herschel, the guy who discovered Uranus. He genuinely believed the sun was inhabited by beings whose heads were specially adapted to the extreme light.
Which sounds absurd to us now.
Totally. They thought the moon had cities on it. They thought Mars was crisscrossed by artificial irrigation canals built by this dying civilization.
And so Danielson and Graney, they posit that the Fermi paradox is essentially modern astrophysics violently waking up from a centuries-old theological hangover. We are finally stripping away that presumption of abundance and actually demanding physical evidence.
And if we strip away that presumption, if life is not a guarantee outcome of cosmic chemistry, we're forced to confront a concept that genuinely keeps me up at night.
The great filter.
Yes. If the universe possesses billions of perfectly habitable, temperate, watery planets, but they're all totally sterile, something must be stopping life from progressing.
Proposed by economist Robin Hanson back in 1996, the great filter is one of the most conceptually terrifying answers to the Fermi paradox.
Because instead of just a generic obstacle course, I actually prefer to think of the great filter as this brutal biological lottery. To get from a barren rock orbiting a young star to a civilization capable of building a Dyson sphere, life has to buy a series of lottery tickets.
And the cost of a ticket is planetary energy and time.
Right. But Hansen argues that somewhere along that evolutionary timeline, there is a lottery with odds so infinitesimally low, almost virtually impossible, that virtually no one ever wins it.
And that specific, nearly impossible leap is the great filter.
It acts as an absolute developmental wall. And the multi-billion-dollar existential question for humanity is the location of that wall.
Right. Are we past it, or is it still in front of us?
That is the question.
Because if the great filter is behind us, it means humanity won a cosmic lottery against staggering odds, and we are one of the few rare survivors in an otherwise totally dead galaxy.
Which is lonely, but great for us.
But if the filter is ahead of us, well, it means our doom, and the doom of literally any civilization that reaches our level of technology is just a statistical certainty.
Unbelievably dark. So, to assess our odds, we have to examine the evolutionary history of Earth and identify candidates for a past great filter. The source text outlines several profound biological leaps.
Yes, the first major candidate is abiogenesis.
Which is the transition from non-living chemical soup to actual living, self-replicating organic matter.
Exactly. And the truth is, we fundamentally do not know the mechanism of abiogenesis. I mean, we can synthesize amino acids in a lab, mimicking early Earth conditions, sure, but getting those acids to spontaneously self-organize into RNA or DNA, it's a complete mystery.
It's a huge leap.
It is entirely possible that the formation of the very first self-replicating molecule was a freak chemical accident, a thermodynamic anomaly with odds of 1 in a trillion.
So if abiogenesis is the great filter, the universe is just filled with oceans of warm water and absolutely nothing swimming in them.
Nothing at all.
But, okay, let's assume life actually starts easily. Let's say basic, single-celled bacteria prokaryotes are just everywhere. The text suggests the next major candidate for the filter is the emergence of eukaryotic cells.
Right. Prokaryotes are simple. They lack a distinct nucleus. And for roughly 2 billion years on Earth, the planet was dominated entirely by this simple slime. Life just stalled out.
2 billion years of just slime.
Exactly. But then, an incredibly unlikely event occurred. Endosymbiosis. One simple cell swallowed another, but instead of digesting it, they formed a symbiotic relationship.
Oh, wow.
And the swallowed cell actually became the mitochondrion, the power plant of the new, highly complex eukaryotic cell.
And without mitochondria, you don't get the energy output required to build multicellular organisms.
No.
You don't get plants, you don't get fungi, you don't get animals.
And astrobiologists debate this fiercely. You have people like Dirk Schultz-McCouch who argue that given enough time and a stable environment, complex transitions like endosymbiosis are just likely to happen eventually.
Sure, it's inevitable.
But then evolutionary biologist Nick Lane points out the staggering difficulty of this specific energy barrier. The rarity of that single cellular merger might be the very reason we don't see alien empires today.
That makes sense. And even if you get animals, the final candidate for a past filter in the text is the evolution of a brain capable of abstract logic and tool use.
Paleobiologist Ola Vin suggests we falsely assume human-level intelligence is the ultimate goal of evolution.
But it's not, right? I mean, evolution is entirely blind.
Completely blind. It has no goal other than immediate survival and reproduction within a very specific ecological niche.
I always think of the great white shark.
Perfect example.
It is an apex predator. It has survived almost unchanged for hundreds of millions of years. It literally survived the asteroid that killed the dinosaurs. It is an absolute evolutionary masterpiece.
But a shark has absolutely no use for calculus or metallurgy or radio waves.
Exactly. A massive, energy-hungry primate brain capable of inventing a spaceship is actually a huge metabolic liability in the wild.
So perhaps the universe is filled with planets teeming with complex, thriving ecosystems, but not a single creature on those planets ever needed to invent a wheel.
But because the mathematics of the Drake equation leave us guessing, and the biological timeline of the Great Filter remains totally theoretical, humanity recognized a necessary pivot.
We had to stop calculating probabilities on chalkboards.
Right, and start actually looking at the sky. A shift from theoretical abstraction to empirical observation. And the very first step in that observational journey was confirming the real estate.
Because up until a few decades ago, astronomers did not know for an absolute fact if other stars even possessed planetary systems.
We assumed they did, but we lacked the optics to prove it.
Until the Kepler Space Telescope.
Yes, Kepler, and later the TESS mission. Those instruments revolutionized astrobiology because they proved that exoplanets are the rule, not the exception.
Now, I want to briefly explain how Kepler actually did this because the mechanics are just fascinating. It used what's called the transit method.
Okay.
Because stars are incredibly bright and planets are incredibly dim and very small, you can't just take a picture of them. So Kepler just stared unblinkingly at a specific patch of the Milky Way, monitoring the light output of over 100,000 stars simultaneously.
Just waiting.
It was looking for a microscopic, periodic dimming of a star's light, an optical eclipse. When a planet crosses the face of its host star from our vantage point, it blocks a minute fraction of the starlight.
And we're talking about a dip in brightness of less than the 100th%, right?
Tiny. But by measuring the frequency and the depth of that dimming, astronomers could calculate the planet's size, its orbital period, and its distance from the star.
And the data Kepler sent back was world-altering. Planets are everywhere. The source document notes that based on observational refinements, current estimates suggest there are between 0.5 to 1.0 potentially habitable planets per star.
Meaning rocky planets orbiting within the Goldilocks zone of their host star.
Not too hot, not too cold.
Right, the specific distance where the temperature allows water to remain liquid on the surface, rather than boiling off into vapor or freezing into solid ice.
So the very first prerequisite of the Fermi paradox is proven beyond a shadow of a doubt. The cosmic real estate is there. There are billions of potentially habitable Earths in our galaxy alone.
The stadium definitely has seats.
The seats are there. So, step 2. We look for the fans. We look for the civilizations.
This is the domain of SETI, the search for extraterrestrial intelligence.
And how exactly did SETI conduct this search historically?
Historically, SETI has relied heavily on radio astronomy, scanning the heavens for anomalous electromagnetic emissions.
Looking for signals.
Yes. The underlying logic is that harnessing the electromagnetic spectrum for communication is a natural, almost inevitable technological bottleneck for any advancing civilization.
Because physics is the same everywhere.
Exactly. Radio waves travel at the speed of light, they pass easily through interstellar dust, and they require relatively little energy to generate.
So SETI has spent decades using these massive radio dishes, like the now collapsed Arecibo Observatory, just listening for non-natural signals.
They were looking for either accidental leakage, which is like the ambient noise of a civilization going about its business, or a deliberate beacon, a high-powered signal intentionally broadcast to say, hey, we are here.
But despite decades of listening across millions of radio channels, the result has been a deafening silence.
Absolute silence.
There have been fleeting anomalies, sure, like the famous wow signal back in 1977, but nothing that repeats, nothing that passes the rigorous scientific threshold for an actual artificial origin.
But let me push back on the leakage idea for a second.
Okay.
If an alien astronomer pointed their radio telescope at our star, the sun, wouldn't they see Earth as this blazing beacon of artificial noise?
Oh, they would certainly detect a highly anomalous radio signature. I mean, since the early 20th century, Earth has been literally bleeding radio frequency energy into space.
Right.
Early high-power television broadcasts, Cold War, early warning radar systems, our global telecommunications networks. We are surrounded by an expanding sphere of radio noise extending roughly 100 light years in every direction.
So if we are radiating all this noise, and there are potentially millions of civilizations out there who have been doing this for thousands of years, shouldn't the galaxy be a cacophony of overlapping radio static?
You would think so, but we hear nothing.
Which forces us to look for larger, more undeniable signatures. If we can't hear their radios, perhaps we can see their infrastructure. We look for stellar-scale artifacts.
Okay, the ultimate sci-fi concept here, Dyson spheres.
Proposed by theoretical physicist Freeman Dyson in 1959. And Dyson didn't base his theory on communication at all. He based it on the ironclad laws of thermodynamics and energy consumption.
Okay.
As a technological civilization grows, its energy requirements increase exponentially. They burn fossil fuels, they harness nuclear fission, they build fusion reactors. But eventually, any expanding civilization will just max out the available resources of their home planet.
They hit a hard energy ceiling.
Exactly. And when they look up, they see a massive fusion-powered battery burning right in the center of their solar system, their host star.
The sun.
Dyson reasoned that a highly advanced civilization, a Kardashev Type 2 civilization, would inevitably construct a megastructure to capture that energy.
How would they even do that?
They would dismantle uninhabitable planets and asteroids to build a dense swarm of energy-gathering satellites, or perhaps even a solid shell, completely enclosing the star to harness its entire radiant output.
Building a shell around a star is engineering on a scale that is almost impossible to even comprehend. But if they did it, how would we detect it? We wouldn't see the metal structure itself, right? It's too far.
No, the structure would be far too small and distant. But we would detect its thermodynamic exhaust.
Okay.
A Dyson sphere absorbs the star's visible light to generate power, but the laws of physics dictate that no process is 100% efficient. That energy must eventually be radiated away as waste heat.
Which means the star's visual light drops, but its infrared signature spikes. It would look like a glowing dark ember in space.
Yes, and we have searched our galaxy for these anomalous infrared signatures.
And the result?
Nothing conclusive.
I have to bring up a specific incident from the source material, though, because it caused absolute chaos in the astronomy community. Back in 2015, data from the Kepler telescope revealed this bizarre behavior in a star named KIC 8462852, colloquially known as Tabby's star.
Oh, yes. The dimming was completely unprecedented.
Because normally, when a Jupiter-sized planet crosses a star, it blocks maybe 1% of the light. But Tabby's star was dimming erratically, unpredictably, and by massive amounts. At one point, 22% of the star's total light was blocked.
Which is huge. The scientific community was initially totally baffled, and the media naturally leaped to the most sensational conclusion: an alien megastructure.
Right.
Perhaps a Dyson swarm mid-construction passing in front of the star.
I admit I was refreshing astrobiology blogs every hour that week. It felt like we'd actually found them.
But penance requires rigor. The source calmly details how further observation resolved the mystery. In 2018, astronomers conducted spectroscopic analysis of Tabby's star during another dimming event. They looked at the light across different wavelengths.
Okay, why does that matter?
Because if a solid, opaque object, like a giant metal alien satellite, was blocking the star, it would block all wavelengths of light equally.
Right. A shadow is a shadow.
Exactly. But the data showed that the dimming varied wildly by frequency. Blue light was blocked significantly more than red light. The only physical phenomenon that produces that specific wavelength filtering is dust.
Oh.
The scientific conclusion was definitive. The erratic dimming of Tabby's star is caused by a massive, irregular cloud of space dust, perhaps the pulverized remains of a destroyed comet or a shattered moon orbiting the star.
Well, a shattered moon is cool, but it's not a Dyson sphere.
No.
So we haven't found megastructures. And there's one final empirical failure we need to discuss before we move into the theories of why the universe is silent. We haven't found their physical probes either.
This is the foundation of the Hart-Tipler conjecture, which relies on the concept of self-replicating von Neumann probes.
Okay, walk me through the mechanics of a von Neumann probe.
Imagine a highly advanced robotic spacecraft equipped with artificial intelligence, an onboard manufacturing plant, and the ability to mine raw materials.
Okay.
A civilization sends this single probe to a neighboring star system. Upon arrival, the AI locates an asteroid, mines the metal and silicates, and uses those materials to build two exact replicas of itself.
It's mechanical cellular division.
Basically, yes. Those two new probes then fire their engines, traveling to two new star systems. They arrive, mine, and build two more copies each. The population of probes grows exponentially. 1 becomes 2, 2 become 4, 4 become 8.
Wow.
With exponential growth, even if these probes travel at a mere 10% the speed of light, they could exhaustively map, explore, and establish a presence in every single star system in the Milky Way within a few million years.
And the text also mentions Bracewell probes as a variation on this.
Yes, a Bracewell probe is designed specifically for communication. Because radio waves take centuries to cross the galaxy, a civilization might send Bracewell probes to lie dormant in distant star systems.
Just waiting.
Waiting, yes. When the probe detects a local species achieving radio technology, the AI wakes up and initiates a conversation, acting as a local ambassador to bypass the agonizing time delay of light-speed communication.
Now, let me push back on the von Neumann probe concept for a second.
Sure.
The assumption is that these machines function flawlessly for millions of years. But any software engineer will tell you that code degrades. When you make a copy of a copy of a copy, billions of times, errors accumulate.
Absolutely.
The AI might mutate. It might forget its original mission. A mutated probe might view other probes as competitors for resources and start a galactic robot war. It's the mechanical equivalent of cancer. Wouldn't exponential mutations stop a von Neumann swarm from conquering the galaxy?
That is a highly valid biological analogy applied to engineering. Mutation and error cascades are a serious threat to any self-replicating system. However, the Hart-Tipler argument counters that by pointing out the sheer scale of probability. Even if 99% of von Neumann swarms succumb to programming errors, resource wars, or mechanical failure, all it takes is one civilization designing a sufficiently robust, error-correcting AI to succeed. If just one civilization in the history of the Milky Way successfully launched a stable swarm, our solar system should be littered with their
We
artifacts.
should see them mining the asteroid belt right now. We should find their dormant Bracewell probes orbiting our moon.
But we have explored our local neighborhood, we have mapped the moon, sent probes to asteroids, and monitored our local radio frequencies. We have found absolutely zero physical evidence of von Neumann or Bracewell probes. The empirical absence is absolute.
So, we've built the stadium, we know it has seats, we've looked with telescopes, we've listened with radio dishes, and we've searched for physical artifacts.
Yes.
Nothing. This forces us to confront the silence head-on. If the math says they should be there, but the evidence says they aren't, our assumptions are deeply flawed. This brings us to the first major category of explanations for the Fermi paradox. What if the universe is empty because life simply does not happen? What if they just don't exist?
This perspective requires a direct, aggressive challenge to the mediocrity principle we discussed in the beginning. It requires us to abandon the idea that Earth is typical. This is the foundation of the rare Earth hypothesis.
Formulated by paleontologist Peter Ward and astronomer Donald Brownlee. They argue that we are suffering from survivorship bias. We look at Earth and think, wow, life is easy. But Ward and Brownlee suggest that Earth is a freakish, 1 in a quintillion statistical anomaly.
Complex life isn't just add water and stir.
Exactly.
The rare Earth hypothesis posits that simple microbial life might be common in the universe, but the evolution of complex, multicellular biological life requires a staggeringly unlikely host of fortuitous compounding circumstances.
The list of requirements in the text is exhausting. First, you need macro-level luck. You have to be in the galactic habitable zone.
Right.
If a solar system is too close to the center of the galaxy, the density of stars exposes planets to lethal doses of radiation from frequent supernovas.
Yeah.
But if you are too far out on the galactic rim, there aren't enough heavy metals synthesized to even form rocky planets.
Then you need planetary level luck. Ward and Brownlee argue that a habitable planet requires highly specific orbital architecture. For instance, the Jupiter factor.
Okay, explain who Jupiter acts as our bodyguard.
Jupiter is a massive gas giant positioned in the outer solar system. Its immense gravitational well acts like a cosmic vacuum cleaner.
Sweeping up debris.
Right. As comets and rogue asteroids hurtle inward from the deep freeze of the Oort cloud toward the inner rocky planets, Jupiter's gravity often intercepts them. It absorbs the impacts or slingshots them safely out of the solar system.
Wow.
Without a Jupiter-like guardian, Earth would be subjected to frequent, sterilizing impacts, preventing life from ever achieving sustained evolutionary complexity.
But it's not just Jupiter. The hypothesis argues we also need our unusually large moon. The moon's gravitational pull stabilizes the Earth's axial tilt. Without it, the Earth might wobble wildly on its axis, causing these catastrophic climate swings that would wipe out fragile ecosystems.
You also need an active planetary geology. Plate tectonics are crucial.
Now, why are earthquakes and volcanoes necessary for life? That seems counterintuitive.
It's about the carbon-silicate cycle. Plate tectonics constantly recycle carbon from the atmosphere down into the Earth's mantle and release it back through volcanic activity. This acts as a long-term planetary thermostat, regulating greenhouse gases and keeping the Earth's surface temperature stable enough for liquid water over millions of years.
Oh, I see.
A planet without plate tectonics, like Mars, loses its ability to regulate its climate.
Furthermore, you need a spinning, liquid iron core to generate a strong magnetic field. The magnetic field acts as a deflector shield against solar wind. Without it, the radiation from the sun would just strip away the atmosphere entirely.
Which is exactly what happened to Mars. It lost its magnetic field as its core cooled, and the solar wind just blew its atmosphere into space.
When you compound all these probabilities, a stable star, the right galactic zone, a Jupiter, a large moon, plate tectonics, a magnetic field, the odds of finding another Earth just plummets drastically.
It's like rolling a 1,000-sided die 100 times and needing it to land on a prime number every single time.
But even if a planet does hit the jackpot, even if it gets the magnetic field and the liquid water, you still have what the text hilariously refers to as the algae versus alumni problem.
I love that. That is a brilliant linguistic summation of an evolutionary bottleneck.
Let's say a planet is a perfect rare Earth duplicate. It forms simple life. How do we know that life won't just remain green algae forever? How do we guarantee the leap from pond scum to university alumni building radio telescopes?
Astrobiologist Charles Lineweaver brought this up with a devastatingly simple point about human hubris. We assume intelligence is the inevitable pinnacle of evolution.
But Lineweaver points out that evolution does not have a destination. There is no biological law of physics dictating that lice must eventually invent microchips.
His prime example is dolphins.
Right.
Dolphins possess massive, highly complex brains. They exhibit intricate social structures. They have regional dialects and language. They demonstrate self-awareness. They are undeniably intelligent.
And they have had tens of millions of years of evolutionary time to build a radio telescope, and they never did.
Because they possess absolutely no biological imperative to do so.
Exactly. They live in a buoyant environment where they are perfectly adapted apex predators. Why would a dolphin invent metallurgy? How could they even harness fire underwater? Evolution optimizes for survival within a niche, not for the capacity to split the atom.
So intelligence does not inevitably lead to technology. We might be alone not because life is rare, but because the specific type of primate intelligence that desires to build machines is incredibly rare.
But there is another dimension to the argument, that they simply don't exist, and it operates on a much grander cosmological timescale. Harvard astrophysicist Avi Loeb suggests an anthropic perspective known as the firstborn hypothesis.
This theory actually offers a strange sense of comfort, I think. It reframes our isolation as a symptom of earliness rather than failure.
We look at the universe being 13.8 billion years old and feel like we missed the party. But Loeb looks at the projected lifespan of the universe.
Right.
The period during which stars will continue to fuse hydrogen and illuminate the cosmos is estimated to last for at least 1 trillion years.
1 trillion years. So 14 billion years is barely the opening act.
Precisely. Furthermore, the early universe was incredibly hostile. It took generations of massive short-lived stars going supernova just to synthesize the heavy elements carbon, oxygen, iron necessary to form rocky planets and complex biological chemistry.
The universe had to cook for billions of years just to generate the raw materials for life.
So under the firstborn hypothesis, humanity isn't late to the cosmic party. We are the very first ones to arrive. We are the hosts putting out the snacks in an empty room, wondering why it's so quiet, completely oblivious to the fact that the actual party doesn't start for another 10 billion years.
We are the early adopters of consciousness in a universe that has only just recently become chemically capable of supporting us.
But the rare earth and firstborn theories assume the universe is a relatively peaceful place once life gets going. The text offers a much darker alternative for why civilizations might be rare: periodic extinction or neocatastrophism.
This is the idea that the cosmos is an inherently violent, dangerous environment. Life might arise frequently across the galaxy, but it is continually eradicated before it can achieve interstellar capacity.
The planetary clock keeps violently resetting, and we know this happens because it happened here. 66 million years ago, a massive asteroid, the Chicxulub impactor, slammed into the Yucatan Peninsula and wiped out the non-avian dinosaurs.
If that rock had missed Earth, mammals might never have inherited the planet, and primates might never have evolved.
And asteroids are just local threats. Neocatastrophism points to galactic-scale sterilization events, such as gamma-ray bursts.
When a massive star collapses into a black hole, it can fire twin beams of unimaginably intense gamma radiation across the galaxy. If one of those beams sweeps across a habitable planet, it instantly vaporizes the ozone layer.
Just gone.
The planet's surface is then baked by ultraviolet radiation from its own sun, triggering a mass extinction.
Or consider internal planetary failures. A young civilization might arise, but natural tectonic shifts cause runaway greenhouse heating, turning their world into a Venusian hellscape. Or volcanic activity triggers complete glaciation, freezing the oceans to the equator.
Neocatastrophism suggests that survival long enough to build a starship is a statistical anomaly in a universe constantly trying to kill you.
Which is a chilling, perfect pivot to our next major area of this discussion. Let's assume the neocatastrophists are wrong. Let's assume civilizations do frequently survive the asteroids and the gamma-ray bursts. They evolve past the algae stage, they develop hands, they invent agriculture, and they build radio telescopes.
Okay, they make it.
But what if they possess an inherent fatal flaw in their sociological or technological evolution? What if the universe is empty because civilizations inevitably destroy themselves?
This is perhaps the most uncomfortable lens through which to view the Fermi paradox, because it serves as a direct mirror to humanity's current geopolitical and environmental precariousness, the theory of self-annihilation.
Astronomer Sebastian von Horner outlined this concept in the early 1960s. He theorized that the rapid progress of science and technology is historically driven by two deeply ingrained psychological factors: the struggle for domination and the desire for an easy life.
And von Horner argued that both of these drives, when amplified by exponential technological capability, lead inexorably to planetary destruction.
It's easy to see his logic. The struggle for domination leads to the development of nuclear arsenals and engineered biological weapons. The desire for an easy life leads to rampant industrialization, rapid resource depletion, and catastrophic environmental collapse.
And what's fascinating here is how the source material delves into a highly rigorous quantitative approach to this environmental collapse. It cites astrophysicist Adam Frank's 2018 climate change models for exocivilizations.
I found Frank's methodology fascinating because it strips away human politics and looks at the problem purely through thermodynamics. You cannot build a global high-energy technological civilization without generating massive amounts of waste heat and chemical byproducts. It is a fundamental law of physics.
Any civilization, alien or human, will interact with and alter its planet's biosphere.
Frank and his team used dynamical systems theory to model this interaction. They mapped population growth and energy consumption against planetary carrying capacity, creating these mathematical trajectories for any young industrial species.
Let's walk through the 4 specific trajectories his model produced, because they map out the potential futures of our own species.
Right. Okay, so what is the first trajectory?
The first trajectory is die-off. In this scenario, the civilization leverages high-impact energy sources, the equivalent of our fossil fuels. Their population explodes, rapidly overshooting the planet's carrying capacity. The biosphere begins to degrade under the thermal and chemical load.
The planet's ecosystem just buckles.
Yes. The civilization realizes the danger, but the environmental collapse triggers a massive population crash. A catastrophic die-off occurs until the population falls back below the diminished carrying capacity, eventually stabilizing at a fraction of its peak.
It's the Mad Max scenario. Humanity survives, but we are scavenging in the ruins.
Yeah.
We certainly aren't building warp drives. Okay, what's the second trajectory?
Sustainability. This is the needle we are currently trying to thread. The civilization recognizes the environmental degradation early. They successfully transition from high-impact to low-impact renewable energy sources. They manage to level off both their population growth and their environmental footprint, reaching a stable, long-term equilibrium with their planet.
The Star Trek scenario. A harmonious, sustainable global society. But the model's next 2 trajectories are where the great filter looms. Trajectory 3.
Collapse without resource change. The population rockets upward, consuming vast amounts of high-impact energy. The planetary environment degrades rapidly. For political or economic reasons, the civilization refuses or fails to transition to sustainable energy.
You just keep burning it.
Right. They cross a thermodynamic tipping point, and the biosphere undergoes a runaway collapse.
The environment becomes utterly uninhabitable, and the civilization doesn't just suffer a die-off, it goes completely extinct. Down to zero.
And the 4th trajectory is perhaps the most tragic from a sociological perspective. Collapse with resource change.
Oh, this one hurts to read. In this scenario, the civilization does recognize the existential threat. They take action. They mandate the transition to sustainable energy. They try to geoengineer a solution. But they started the transition too late.
The environmental feedback loops, the melting of ice caps, the release of trapped methane, the acidification of oceans have already been triggered.
The momentum of the collapse is locked in. The civilization tries to save itself, but the planet dies anyway, taking the species with it.
Adam Frank's work fundamentally reframes the Fermi paradox. Driving catastrophic climate change might not be a unique failing of human greed. It might be a generic, nearly unavoidable thermodynamic bottleneck for any energy-intensive civilization in the cosmos.
The lead physicist, Stephen Hawking, viewed this exact same bottleneck of self-destruction, but he analyzed it through a slightly different lens. He focused on the disparity between biological and technological evolution.
Hawking identified a critical juncture he called the external transmission phase.
Explain how Hawking defined that.
Well, for billions of years, the evolution of life is entirely biological. Information is passed from one generation to the next via DNA. It is a painstakingly slow, trial-and-error process determined by natural selection. But eventually, an intelligent species invents language, writing, and the scientific method. They enter the external transmission phase.
Knowledge is no longer trapped in the genome. It is stored externally in books, libraries, and eventually digital servers.
Exactly. And while biological evolution continues at a glacial pace, the accumulation of external knowledge grows exponentially. The core problem, Hawking argued, is that our biological instincts, our Paleolithic aggression, our tribalism, our territoriality remain completely static, while our technological power to act on those instincts becomes godlike.
We have the emotional regulation of cavemen, but we are handing those cavemen thermonuclear warheads and artificial intelligence.
It creates a system that is inherently unstable. Hawking deeply feared that a civilization in this transition phase is incredibly vulnerable. Our ability to invent the tools of our own annihilation, whether it be weaponized artificial general intelligence, engineered global pandemics, or antimatter weapons, vastly outpaces our collective wisdom and political maturity to safely manage them.
Therefore, Hawking reasoned, civilizations naturally destabilize and destroy themselves long before they possess the stability required to master interstellar travel.
Okay, self-annihilation is a heavy concept,
Yeah,
but the source material contains a theory that is arguably even more terrifying. What if a civilization doesn't destroy itself? What if they survive the climate crisis, they manage their AI, they look out at the stars, and they realize the universe is full of other civilizations?
this brings us to the dark forest hypothesis.
A concept that relies heavily on game theory and the tragedy of the commons, frequently explored in hard science fiction.
The source explicitly cites sci-fi authors who have done the theoretical heavy lifting on this, specifically Greg Bear's The Forge of God and Lou Sixon's The Three-Body Problem. I want to lay out the logic of the dark forest, and you tell me if the game theory holds up.
Proceed. Let's hear it.
Imagine you are a young, newly interstellar civilization. Your primary goal, above all else, is the survival of your species. You build a telescope, and you detect another alien civilization 50 light years away. You have to decide what to do. You might think, let's send a message and be friends. But you realize you cannot guarantee their intentions. They might be peaceful, or they might be hyper-aggressive expansionists.
The chain of suspicion is initiated.
Right. And because of the speed of light limit, communication takes decades. You can never have a real-time diplomatic dialogue to ease that suspicion. Furthermore, you face the problem of technological explosion. A civilization might seem primitive today, but in the 100 years it takes to send a message back and forth, they could undergo a technological singularity and possess weapons capable of destroying your sun.
Therefore, the risk of engagement is absolute annihilation.
Exactly. The game theory dictates that the most rational, prudent, mathematically safe action to guarantee your own survival is to immediately and silently exterminate any nascent life form you detect before they can perceive you and become a threat. You strike first with overwhelming force, usually a relativistic kill vehicle that destroys their planet without warning.
The logic, grim and paranoid as it is completely sound within a framework where resources are finite, intentions are unknowable, and the speed of light enforces isolation.
This reframes the entire Fermi paradox. Space isn't an empty, sterile stadium. Space is a dark forest. Every surviving civilization is an armed hunter stalking through the trees, holding their breath, masking their thermal signature. If a hunter spots a campfire or hears another creature moving, they don't call out to say hello, they instantly pull the trigger.
In Lou Sixon's framework, the galaxy is utterly silent because everyone is terrified of being noticed. The great silence is the sound of predators hiding.
And how do these hunters pull the trigger? That brings us back to the robotic probes we discussed earlier, but repurposed for genocide. Fred Saberhagen termed them berserkers.
The ultimate preemptive strike. You don't risk sending your own people into the dark forest. You engineer a self-replicating von Neumann probe, but instead of giving it a mission to explore and communicate, you program it with one simple, immutable directive. Locate biological life and sterilize it.
A single advanced civilization could unleash a swarm of berserker probes that sweep across the galaxy, automatically extinguishing any civilization the moment it begins emitting radio waves or altering its atmosphere.
Which casts humanity's current behavior in an incredibly foolish light. We are doing the exact opposite of hiding.
We really are. We stacked golden records with maps to Earth on the Voyager probes. We beamed the Arecibo message directly at star clusters. We've been broadcasting a sphere of radar and television signals for a century. To quote Greg Bear from the text, we're acting like an infant lost in a dark forest, crying our hearts out, wondering why no one is answering, completely oblivious to the fact that our cries are just drawing down the wolves.
If the dark forest hypothesis holds true, the silence of the universe is not an absence of life. It is an evolved survival tactic.
Okay, deep breath. We need a palate cleanser from the homicidal robotic wolves. Let's pivot. Let's explore the possibility that the galaxy is not a paranoid war zone, and civilizations don't inevitably nuke their own atmosphere. What if the galaxy is thriving, peaceful, and heavily populated, but our fundamental human assumptions about how advanced civilizations behave, communicate, and expand are just completely wrong?
This requires us to look at the paradox through the lens of advanced economics, physics, and planetary science. We must consider the possibility that we just can't see them.
Let's start with the economic argument, the concept of information versus matter, and the Jevons paradox. The text cites an analysis by Louis K. Scheffer, who mathematically breaks down why building a sci-fi galactic empire is a colossal waste of resources.
It comes down to the thermodynamic efficiency of transmission. Scheffer calculated the energy required to physically accelerate a mass, say, a spaceship carrying biological organisms to interstellar speeds. He then compared that to the energy required to transmit the equivalent amount of data across the same distance using electromagnetic waves.
And the cost difference is staggering.
Scheffer calculates that transmitting information across the galaxy is anywhere from 100 million to 100 quadrillion times cheaper in terms of sheer energy than physically transferring matter.
100 quadrillion times cheaper.
Yeah.
So apply that to the Fermi paradox. We expect aliens to behave like humans in Star Trek, building massive metal starships, filling them with biological bodies, burning unbelievable amounts of fuel, and physically traveling to new planets to mine rocks and build cities. But you're saying a truly advanced civilization would look at that and think it's primitive. They might just email their consciousness across the galaxy.
Exactly. Why spend a planetary energy budget to send the fragile biological meat when you can send the digital mind for fractions of a penny? If a civilization transitions to a post-biological state, if they become a machine intelligence, or learn how to upload their consciousness into digital substrates, physical travel becomes obsolete.
How does a galactic internet of minds actually work?
The first civilization to achieve this might send out slow, automated robotic probes one time, just to set up receiver nodes on distant, resource-rich worlds. Once that physical network is in place, the civilization never travels again. They simply beam their consciousness as dense packets of data from node to node at the speed of light.
Okay, but if the galaxy is crisscrossed by a hyper-advanced internet beaming trillions of digital alien minds back and forth, shouldn't our radio telescopes detect that data traffic?
Not if they are prioritizing efficiency. This communication would be highly directed point-to-point transmission, likely using lasers or high-frequency microwaves at the absolute minimum power required to prevent signal degradation. It wouldn't be a loud, omnidirectional radio broadcast spilling sloppily out into the void. It would be an incredibly tight, invisible beam.
So if we aren't directly in the beam's path,
If Earth's orbit doesn't cross directly into the exact path of that microscopic laser beam, we would be completely oblivious to the network.
the text ties this to the Jevons paradox.
Yes, the Jevons paradox is an economic principle observed heavily on Earth. It states that as technological progress increases the efficiency with which a resource is used, the rate of consumption of that resource actually rises because it becomes economically cheaper to use.
So an advanced civilization doesn't necessarily achieve a Zen-like state of low energy consumption. They might consume the energy of an entire star, but their technology is so incredibly efficient, so densely engineered, that there is zero thermodynamic leakage for us to detect. Their footprint is dense, not loud.
Which naturally leads to the next theory in the text, virtual worlds and estivation. If a civilization values data over physical matter, they might entirely abandon the physical universe. Avi Loeb and Nick Bostrom suggest that an advanced society might just upload themselves into a massive utopian virtual reality.
The ultimate inward turn. Think about our own human trajectory. We spend thousands of years conquering our physical needs, securing food, building shelter, mastering survival. Once survival is guaranteed, what does humanity immediately invent? Entertainment. Escapism. We build the internet, immersive video games, virtual reality headsets. We are already spending huge portions of our lives interacting with screens rather than physical nature.
The theory extrapolates that human trend to a species capable of building a Matryoshka brain, a megastructure computer powered by a star.
Why explore a cold, dangerous, irradiated universe restricted by the agonizingly slow speed of light when you can upload your mind into a simulated universe where you control the laws of physics? In a virtual world, you can live as a god, experience limitless pleasure, and simulate any reality instantly. The psychological appeal of a perfected virtual contrivance would inevitably overtake any desire to deal with the harsh, expensive reality of space exploration.
They aren't dead, and they haven't destroyed themselves. They are just all logged in permanently, running infinite simulations, completely disinterested in the physical void outside their servers.
That makes a chilling amount of sense. But let's look at civilizations that are still biological. What if an alien species is highly intelligent, possesses a deep desire to explore the stars, but is physically trapped on their home world by the brutal realities of chemistry and planetary science?
We must consider environmental traps. The most fascinating of these is the oxygen bottleneck proposed by Amedeo Balbi and Adam Frank.
This blew my mind because it focuses on the unyielding chemical prerequisites for industrialization.
To build a spaceship, a civilization requires metal. To obtain usable metal, you must smelt raw ore. To smelt ore, you require sustained high-temperature fire. And to create fire, you require a highly specific atmospheric composition.
Specifically oxygen. Earth's atmosphere currently sits at roughly 21% oxygen. It is the perfect mixture. It's high enough to allow wood and coal to burn hot enough to smelt copper and iron, but not so high that the entire planet's forests spontaneously combust.
Balbi and Frank calculated the physics of combustion. They determined that you need an atmosphere of at least 18% oxygen to sustain the kind of open-air combustion necessary to initiate metallurgy and industrial revolution.
The threshold is incredibly rigid. So run the thought experiment. Imagine an Earth-like planet with a thriving biosphere, but its atmosphere stabilizes at 15% oxygen. Complex life evolves. A highly intelligent bipedal species emerges. They build complex societies, they develop philosophy, mathematics, and agriculture. But when they try to strike a spark to burn a pile of wood, it just smolders and dies. They can never, ever start a forge.
They are technologically gated by their own atmosphere. They are permanently trapped in the Stone Age, entirely invisible to our radio telescopes, not because they lack intelligence, but because the chemistry of their air forbids industry.
David Brin expanded on this environmental trap with his water worlds hypothesis. Earth is actually quite dry. We have 32% continental mass protruding above sea level. But what if the average habitable planet in the galaxy is a super-Earth, almost entirely covered in deep global oceans?
The evolution of terrestrial creatures with hands capable of harnessing fire would be virtually non-existent.
Brin suggests the galaxy might be teeming with intelligent life, but they are aquatic. Brilliant octopuses, dolphins, and whales. They might possess rich oral cultures, complex social structures, and sonar-based languages. But you cannot smelt iron underwater. You cannot discover electricity in a saltwater ocean without electrocuting yourself. They are brilliant, but they are physically prevented from ever building a rocket.
Planetary scientist Alan Stern takes this aquatic trap one step further, focusing not on surface oceans, but on subsurface oceans.
Right? Environments like Jupiter's moon Europa or Saturn's moon Enceladus.
Stern argues that the majority of habitable liquid water in the universe might not reside on the surface of temperate planets. It might be locked deep underground beneath miles of solid planetary crust or thick ice sheets, kept warm by tidal friction or geothermal vents.
Evolutionarily, a subsurface ocean is a fantastic place to live. You are completely insulated from the horrors of the cosmos. Asteroid impacts, gamma-ray bursts, solar flares. None of it matters when you live beneath 10 miles of solid ice. The environment is incredibly stable for billions of years.
It is a sanctuary for life, but it is an absolute prison for a technological civilization.
Think about the psychology of a species evolving in a dark ocean beneath 10 miles of ice. They have no concept of a sky. They have no concept of stars or a universe beyond their watery ceiling. Their entire cosmos is the ocean floor and the ice roof. And even if they develop hyperintelligence, harness geothermal energy, and build a thriving civilization, the sheer engineering challenge of tunneling up through miles of freezing, shifting ice into the lethal vacuum of space is virtually insurmountable.
And from our perspective, looking out, we would never detect them. Their acoustic communication doesn't transmit through the vacuum of space, and any low-frequency radio waves they might accidentally generate would never penetrate the thick shell of ice and water shielding their world. The galaxy could be teeming with billions of thriving aquatic civilizations, and we're all just completely isolated in our own little opaque bubble.
Right. That is a profoundly lonely thought. But there is one final category of explanations we must explore. If civilizations haven't destroyed themselves, if they haven't uploaded into virtual reality, and if they aren't trapped beneath the ice, we must confront the possibility that they are out there, they are fully aware of us, and they are making a conscious, deliberate choice to leave us alone.
We're entering the realm of the zoo hypothesis and the SETI paradox.
Proposed by John Ball in 1973, the zoo hypothesis suggests exactly what the name implies. Extraterrestrial life exists, it is highly advanced, and it knows exactly where Earth is. But they have placed us in a cosmic nature reserve.
They have adopted a strict look but don't touch policy. They're observing our natural biological evolution and our sociological development, much like human anthropologists observing an uncontacted tribe in the Amazon basin.
The prime directive from Star Trek. They refuse to interfere until we reach a certain technological or moral threshold. But from a purely logical standpoint, the zoo hypothesis has a massive, glaring flaw. The text calls it the problem of the uniformity of motive.
Yes. For the zoo hypothesis to explain the absolute silence of the Fermi paradox, it requires flawless, unanimous compliance across vast stretches of time and space. Let's assume there are 1,000 advanced civilizations in the galaxy. For the quarantine of Earth to hold, every single one of those 1,000 civilizations must perfectly agree to obey the quarantine.
And it's not just the governments. Every single faction within those civilizations, every corporation, every religious cult, and every rogue alien teenager with access to a faster-than-light joyride must perfectly obey the rules.
Yeah.
It only takes one idiot in a flying saucer to break the quarantine and land on the White House lawn, and the illusion is shattered forever.
The probability of achieving perfect, unanimous adherence to a non-interference policy decreases exponentially as the number of actors in the galaxy increases. Human history proves that uniformity of motive is practically impossible to maintain.
However, the text does offer two mechanisms that could theoretically enforce a galactic quarantine.
First is the concept of a hegemonizing artificial intelligence. If galactic politics are dominated not by squabbling biological empires, but by a single, unimaginably powerful artificial superintelligence that physically enforces the law. If a rogue alien ship tries to visit Earth to break the quarantine, the AI simply vaporizes it before it enters our solar system.
The galaxy has a bouncer. What's the second mechanism?
The cultural founder effect. This ties back to the firstborn hypothesis. If the very first civilization to achieve interstellar travel establishes a deep cultural norm of non-interference, and they have a million-year head start on everyone else, they possess the power to dictate the culture of the entire galaxy. As younger civilizations emerge, they are assimilated into this prevailing culture. They set the rules of the zoo, and everyone else falls in line because the founders are functionally gods to them.
Let's assume there is no grand galactic federation enforcing a zoo. What if everyone is just sitting alone in their rooms, too scared to speak? This brings up the SETI paradox.
Also referred to in astrobiology as the fear of contact.
The paradox highlights the profound hypocrisy of humanity's current approach to the cosmos. We are spending massive amounts of time, computing power, and money listening for signals from the stars. But within the scientific community, we are extremely hesitant to actually transmit a deliberate, powerful signal ourselves.
We are eager to find them, but we are terrified of being found.
Exactly. And why are we terrified? Because we understand the dark forest logic. We understand our own violent history. So apply the mediocrity principle here. If every civilization that achieves radio technology reaches the exact same logical conclusion that listening is scientifically rewarding but broadcasting is potentially suicidal, then the entire galaxy is full of eager listeners sitting in dead silence, waiting for a caller who never dials.
This hesitation is not merely theoretical. The source text notes that within the human scientific and political community, there is absolutely no consensus on whether we should reply if we ever do detect a definitive alien signal.
The official SETI protocol is essentially a bureaucratic nightmare. It states that if a signal is confirmed, no response should be sent until appropriate international consultations take place. Human governments cannot even agree on basic carbon emission treaties. Imagine the geopolitical chaos of trying to agree on who gets to draft the first diplomatic message to an alien empire.
A cautious alien decision-maker, observing human history, would note that when a technologically advanced civilization makes contact with a less advanced culture, the results for the less advanced culture are almost universally disastrous. They might simply conclude that initiating contact is a lose-lose scenario.
Before we wrap up this massive deep dive, we have to briefly address the elephant in the room regarding the "they are ignoring us" category, the conspiracy angle, the extraterrestrial UFO hypothesis. A significant vocal portion of the public firmly believes the Fermi paradox is a lie. They believe the aliens are already here, zipping around our airspace in tic-tac-shaped craft, and the governments of the world are engaged in a massive cover-up.
The source material is unequivocal regarding the scientific consensus on this matter.
Right. The text acknowledges that unidentified anomalous phenomena UAPs are real physical events that are fascinating and absolutely deserve rigorous, destigmatized scientific investigation. However, the overwhelming consensus in the scientific literature is that there is no convincing empirical evidence linking these phenomena to extraterrestrial spacecraft.
Leaping from, we cannot identify this radar anomaly, to, this is an interstellar vessel piloted by non-human intelligence, is a failure of scientific epistemology.
Furthermore, the scientists actually involved in SETI dismiss the idea of a successful long-term government suppression of a real alien signal.
It fundamentally misunderstands how astronomy works. Observatories are globally distributed and largely run by academic institutions, not the military. If a confirmed alien signal came in, the scientists involved would leak it instantly out of sheer, overwhelming excitement.
The greatest discovery in the history of human civilization is not something an astronomer is going to quietly file away in a manila folder just because a government agent asked them to.
So we must trust the silence. The data tells us the galaxy is quiet.
And that quiet is deafening. We have covered an immense amount of ground today. We've explored the math of the Drake equation, the empirical failure to find radio waves or Dyson spheres. We've debated the rare Earth hypothesis, the great filter, the existential dread of the dark forest, the thermodynamic efficiency of uploading into virtual worlds, the tragic reality of squids trapped under ice, and the paranoia of the galactic zoo. So, looking at this entire mountain of source material, what is the core takeaway for the listener? How do we synthesize the Fermi paradox?
The Fermi paradox is ultimately not about aliens. It is a mirror reflecting our own anxieties, our own frailties, and our own perilous stage of development. It forces us to ask critical, uncomfortable questions about the nature of humanity. Are we a fragile, miraculous anomaly that needs to be fiercely protected, as the rare Earth hypothesis suggests? Are we a ticking time bomb rapidly approaching a great filter of our own making through climate collapse and weaponized technology? Or are we oblivious, noisy toddlers wandering through a dangerous cosmic forest, desperately needing to learn caution? The paradox does not provide us with answers. Instead, it forces profound critical thinking about our own technological adolescence. The silence of the universe is a stark, echoing demand that we figure out how to survive ourselves.
That is a phenomenal synthesis. The silence isn't an absence, it's a warning. And that leads perfectly into the final thought I want to leave you with today. We have spent this entire deep dive looking outward. We've been looking at distant stars, analyzing the atmospheres of exoplanets, and debating the psychological motivations of hypothetical galactic empires. But tonight, when you step outside and look up at the stars, I want you to turn the paradox inward. The source material briefly mentions a fringe concept called the planetarium hypothesis.
An extension of the simulation argument.
Yes, it's the idea that the universe appears empty because it was designed to look empty. Building on the economic concept we discussed earlier, that information is vastly cheaper than matter, and that advanced beings might prefer to exist in highly engineered virtual worlds. Consider your own daily life. Consider how much time you spend looking at a screen, immersed in a digital reality rather than interacting with the physical world. What if the apex of technological evolution is total simulation? What if you are in the simulation? What if the great silence isn't a vast, lonely cosmos, but a localized, incredibly complex quarantine of the mind? What if the universe appears totally, terrifyingly empty of other life, because this specific, highly detailed reality was rendered solely to observe what a conscious mind does when it believes it is completely, utterly alone? Thank you so much for joining us on this custom-tailored deep dive into the Fermi paradox. Stay insanely curious. We'll catch you next time.